A railgun is a device that uses electromagnetic force to launch high-velocity projectiles, by means of a sliding armature that is accelerated along a pair of conductive rails. It is typically constructed as a weapon and the projectile normally does not contain explosives, relying on the projectile's high speed to inflict damage. The railgun uses a pair of parallel conductors, or rails, along which a sliding armature is accelerated by the electromagnetic effects of a current that flows down one rail, into the armature and then back along the other rail. It is based on principles similar to those of the homopolar motor. Railguns are being researched as weapons that use electromagnetic forces to impart a very high kinetic energy to a projectile, e.g. APFSTs, rather than using conventional propellants. While explosive-powered military guns cannot readily achieve a muzzle velocity of more than about 2 km per second, railguns can readily exceed 3 km per second. For a similar projectile, the range of railguns may exceed that conventional guns. The destructive force of a projectile depends on its kinetic energy at the point of impact, and due to the potentially large velocity of a railgun-launched projectile, their destructive force may be much greater than conventionally launched projectiles of the same size. The absence of explosive propellants or warheads to store and handle, as well as the low cost of projectiles compared to conventional weaponry, come as additional advantages. Notwithstanding the above advantages, railguns are still very much at the research stage, and it remains to be seen whether or not railguns will ever be deployed as practical military weapons. Any trade-off analysis between electromagnetic, propulsion systems and chemical propellants for weapons applications must also factor in the novelty and complexity of the pulsed power supplies that are needed for electromagnetic launcher systems. In addition to military applications, NASA has proposed to use a railgun to launch wedge-shaped aircraft with scramjets to high altitude at Mach 10, where they will then fire a small payload into orbit using conventional rocket propulsion. The extreme G-forces involved with direct railgun ground launch to space may restrict the usage to only the sturdiest of payloads. Alternatively, very long rail systems may be used to reduce the required launch acceleration. Basics. In its simplest, and most commonly used, form, the railgun differs from a traditional electric motor in that no use is made of additional field windings, or permanent magnets. This basic configuration is formed by a single loop of current and thus requires high currents, e.g., of order 1 million amperes, to produce sufficient accelerations, and muzzle velocities. A relatively common variant of this configuration is the augmented railgun, in which the driving current is channeled through additional pairs of parallel conductors, arranged to augment, the magnetic field experienced by the moving armature. These arrangements reduce the current required for a given acceleration. In electric motor terminology, augmented railguns are usually series wound configurations. Some railguns also use strong neodymium magnets with the field perpendicular to the current flow to increase the force on the projectile. The armature may be an integral part of the projectile, but it may also be configured to accelerate a separate, electrically isolated or non-conducting projectile. Solid, metallic sliding conductors are often the preferred form of railgun armature, but plasma or hybrid armatures can also be used. A plasma armature is formed by an arc of ionized gas that is used to push a solid, non-conducting payload in a similar manner to the propellant gas pressure in a conventional gun. A hybrid armature uses a pair of plasma contacts to interface a metallic armature to the gun rails. Solid armatures may also transition into hybrid armatures, typically after a particular velocity threshold is exceeded. A railgun requires a pulsed DC power supply. For potential military applications, railguns are usually of interest because they can achieve much greater muzzle velocities than guns powered by conventional chemical propellants. Increased muzzle velocities with better aerodynamically streamlined projectiles can convey the benefits of increased firing ranges, while, in terms of target effects, increased terminal velocities can allow the use of kinetic energy rounds incorporating hit-to-kill guidance, as replacements for explosive shells. Therefore, typical military railgun designs aim for muzzle velocities in the range of 2030-500 m/s with muzzle energies of 550 MJ. For comparison, 50 mj is equivalent to the kinetic energy of a school bus weighing 5 metric tons, traveling at 509 km per hour, 316 miles per hour. For single-loop railguns, these mission requirements require launch currents of a few million amperes, so a typical railgun power supply might be designed to deliver a launch current of 5 mA for a few milliseconds. As the magnetic field strengths required for such launches will typically be approximately 10 Tesla, 100 kilogauss, most contemporary railgun designs are effectively air-cored, i.e., they do not use ferromagnetic materials such as iron to enhance the magnetic flux. However, if the barrel is made of a magnetically permeable material, the magnetic field strength increases due to the increase in permeability, μ equals μ0 asterisk μr, where μ is the effective permeability, μ0 is the permeability constant and μr is the relative permeability of the barrel. This automatically increases the force. Railgun velocities generally fall within the range of those achievable by two-stage light gas guns, however, the latter are generally only considered to be suitable for laboratory use, while railguns are judged to offer some potential prospects for development as military weapons. Another light gas gun, the Combustion Light Gas Gun in a 155 mm prototype form was projected to achieve 2,500 m/s with a .70 caliber barrel. In some hypervelocity research projects, projectiles are pre-injected into railguns, to avoid the need for a standing start, and both two-stage light gas guns and conventional powder guns have been used for this role. In principle, if railgun power supply technology can be developed to provide safe, compact, reliable, combat survivable, and lightweight units, then the total system volume and mass needed to accommodate such a power supply and its primary fuel can become less than the required total volume and mass for a mission-equivalent quantity of conventional propellants and explosive ammunition. Arguably, such technology has been matured with the introduction of the Electromagnetic Aircraft Launch System, EMLS, albeit that railguns require much higher system powers, because roughly similar energies must be delivered in a few milliseconds, as opposed to a few seconds. Such a development would then convey a further military advantage in that the elimination of explosives from any military weapons platform will decrease its vulnerability to enemy fire. History. The earliest electromagnetic gun developed was the coil gun. Its development reportedly started in 1845. The first patent was awarded to Professor Christian Birkeland of the University of Christiania, today Oslo. He accelerated a 500 grams projectile to 50 m/s. In 1918, French inventor Louis-Octave Fauconville created an electric cannon. He filed for a U.S. patent on April 1, 1919, which was issued in July 1922 as patent number 1,421,435 electric apparatus for propelling projectiles. In his device, two parallel busbars are connected by the wings of a projectile, and the whole apparatus surrounded by a magnetic field. By passing current through busbars and projectile, a force is induced which propels the projectile along the busbars and into flight. In 1944, during World War II, Joachim Hansler of Germany's Ordnance Office proposed the first theoretically viable railgun. By late 1944, the theory behind his electric anti-aircraft gun had been worked out sufficiently to allow the Luftwaffe's Flak Command to issue a specification, which demanded a muzzle velocity of 2,000 m/s, 6,600 feet/s, and a projectile containing 0.5 kilograms, 1.1 pounds, of explosive. The guns were to be mounted in batteries of 6 firing 12 rounds per minute, and it was to fit existing 12.8 cm Flak 40 mounts. It was never built. When details were discovered after the war, it aroused much interest and a more detailed study was done, culminating with a 1947 report which concluded that it was theoretically feasible, but that each gun would need enough power to illuminate half of Chicago. During 1950, Sir Mark Oliphant, an Australian physicist and first director of the Research School of Physical Sciences at the New Australian National University, initiated the design and construction of the world's largest, 500 megajoule, homopolar generator. This machine was operational from 1962 and was later used to power a large-scale railgun that was used as a scientific experiment. Since 1993, the British and American governments have collaborated on a railgun project at the Dundrennan Weapons Testing Centre that culminated in the 2010 test where B systems fired a 3.2 kg, 7-pound, projectile at 33 megajoules. In 1994, India's DRDO's Armament Research and Development Establishment developed a railgun with a 240 kJ, low-inductance capacitor bank operating at 5 kV power, able to launch projectiles of 3 to 3.5 grams weight to a velocity of more than 2.00 km per second. In 2010, the United States Navy tested a B Systems-designed compact-sized railgun for ship emplacement that accelerated a 3.2 kg, 7-pound, projectile to hypersonic velocities of approximately 2.4 km per second, 8,600 km per hour, or about Mach 7, with 33 megajoules of kinetic energy. It was the first time in history that such levels of performance were reached. They gave the project the motto Velocitas Erradico, Latin for speed, eradicate, or in the vernacular, speed kills. An earlier railgun of the same design, 32 megajoules, resides at the Dundrennan Weapons Testing Centre in the United Kingdom. Low-power, small-scale railguns have also made popular college and amateur projects. Several amateurs actively carry out research on railguns. Examples can be found on YouTube. Design. Theory. A railgun consists of two parallel metal rails, hence the name, connected to an electrical power supply. When a conductive projectile is inserted between the rails, at the end connected to the power supply, it completes the circuit. Electrons flow from the negative terminal of the power supply up the negative rail, across the projectile, and down the positive rail, back to the power supply. This current makes the railgun behave as an electromagnet, creating a magnetic field inside the loop formed by the length of the rails up to the position of the armature. In accordance with the right-hand rule, the magnetic field circulates around each conductor. Since the current is in the opposite direction along each rail, the net magnetic field between the rails, B, is directed at right angles to the plane formed by the central axes of the rails and the armature. In combination with the current, I, in the armature, this produces a Lorentz force which accelerates the projectile along the rails, always out of the loop, regardless of supply polarity, and away from the power supply. There are also Lorentz forces acting on the rails and attempting to push them apart, but since the rails are mounted firmly, they cannot move. By definition, if a current of 1 ampere flows in a pair of ideal infinitely long parallel conductors that are separated by a distance of 1 meter, then the magnitude of the force on each meter of those conductors will be exactly 0.2 micronewtons. Furthermore, in general, the force will be proportional to the square of the magnitude of the current and inversely proportional to the distance between the conductors. It also follows that, for railguns with projectile masses of a few kg and barrel lengths of a few m, very large currents will be required to accelerate projectiles to velocities of the order of 1000 m/s. A very large power supply, providing on the order of 1 million amperes of current, will create a tremendous force on the projectile, accelerating it to a speed of many kilometers per second, km/s. Although these speeds are possible, the heat generated from the propulsion of the object is enough to erode the rails rapidly. Under high-use conditions, current railguns would require frequent replacement of the rails, or to use a heat-resistant material that would be conductive enough to produce the same effect. At this time it is generally acknowledged that it will take major breakthroughs in materials science and related disciplines to produce high-powered railguns capable of firing more than a few shots from a single set of rails. The barrel must withstand these conditions for up to several rounds per minute for thousands of shots without failure or significant degradation. These parameters are well beyond the state-of-the-art in materials science. Mathematical formula. This section presents some elementary analysis of the fundamental theoretical electromagnetic principles that govern the mechanics of railguns. Design considerations. The power supply must be able to deliver large currents, sustained and controlled over a useful amount of time. The most important gauge of power supply effectiveness is the energy it can deliver. As of December 2010, the greatest known energy used to propel a projectile from a railgun was 33 megajoules. The most common forms of power supplies used in railguns are capacitors and compulsators, which are slowly charged from other continuous energy sources. The rails need to withstand enormous repulsive forces during shooting, and these forces will tend to push them apart and away from the projectile. As rail/projectile clearances increase, arcing develops, which causes rapid vaporization and extensive damage to the rail surfaces and the insulator surfaces. This limited some early research railguns to 1 shot per service interval. The inductance and resistance of the rails and power supply limit the efficiency of a railgun design. Currently, different rail shapes and railgun configurations are being tested, most notably by the U.S. Navy, Naval Research Laboratory, the Institute for Advanced Technology at the University of Texas at Austin, and B Systems. Materials used. The rails and projectiles must be built from strong conductive materials. The rails need to survive the violence of an accelerating projectile, and heating due to the large currents and friction involved. Some erroneous work has suggested that the recoil force in railguns can be redirected or eliminated. Careful theoretical and experimental analysis reveals that the recoil force acts on the breech closure just as in a chemical firearm. The rails also repel themselves via a sideways force caused by the rails being pushed by the magnetic field, just as the projectile is. The rails need to survive this without bending and must be very securely mounted. Currently published material suggests that major advances in material science must be made before rails can be developed that allow railguns to fire more than a few full power shots before replacement of the rails is required. Heat dissipation. In current designs, massive amounts of heat are created by the electricity flowing through the rails, as well as by the friction of the projectile leaving the device. This causes 3 main problems: melting of equipment, decreased safety of personnel, and detection by enemy forces due to increased infrared signature. As briefly discussed above, the stresses involved in firing this sort of device require an extremely heat-resistant material. Otherwise, the rails, barrel, and all equipment attached would melt or be irreparably damaged. In practice, the rails used with most railgun designs are subject to erosion from each launch. Additionally, projectiles can be subject to some degree of ablation, and this can limit railgun life, in some cases severely. Applications. Railguns have a number of potential practical applications, primarily for the military. However, there are other theoretical applications currently being researched. Launch or launch assist of spacecraft. Electrodynamic assistance to launch rockets has been studied. Space applications of this technology would likely involve specially formed electromagnetic coils and superconducting magnets. Composite materials would likely be used for this application. For space launches from Earth, relatively short acceleration distances, less than a few km, would require very strong acceleration forces, higher than humans can tolerate. Other designs include a longer helical, spiral, track, or a large ring design whereby a space vehicle would circle the ring numerous times, gradually gaining speed, before being released into a launch corridor leading skyward. Nevertheless, if technically feasible and cost-effective to build, imparting hypervelocity escape velocity to a projectile launching at sea level, where the atmosphere is the most dense, may result in much of the launch velocity being lost to aerodynamic drag. In addition, the projectile might still require some form of onboard guidance and control to realize a useful orbital insertion angle that may not be achievable based simply on the launcher's upward elevation angle relative to the surface of the Earth. See practical considerations of escape velocity. In 2003, Ian McNabb outlined a plan to turn this idea into a realized technology. Because of strong acceleration, this system would launch only sturdy materials, such as food, water, and most importantly fuel. Under ideal circumstances, equator, mountain, heading east, the system would cost $5.28/kg, compared with $5,000/kg on the conventional rocket. The McNabb's railgun could make approximately 2,000 launches per year, for a total of maximum 500 tons launched per year. Because the launch track would be 1.6 kilometers long, power will be supplied by a distributed network of 100 rotating machines, compulsator, spread along the track. Each machine would have a 3.3-ton carbon fiber rotor spinning at high speeds. A machine can recharge in a matter of hours using 10 MW power. This machine could be supplied by a dedicated generator. The total launch package would weigh almost 1.4 tons. Payload per launch in these conditions is over 400 kilograms. There would be a peak operating magnetic field of 5 T, half of this coming from the rails, and the other half from augmenting magnets. This halves the required current through the rails, which reduces the power fourfold. Weaponry. Railguns are being researched as weapons with projectiles that do not contain explosives or propellants, but are given extremely high velocities, 2,500 m/s, 8,200 feet/s, approximately Mach 7 at sea level, or more. For comparison, the M16 rifle has a muzzle speed of 930 m/s, 3,050 feet/s, and the 16/50 caliber Mark 7 gun that armed World War II American battleships has a muzzle speed of 760 m/s, 2,490 feet/s, which because of its much greater projectile mass, up to 2,700 pounds, generated a muzzle energy of 360 mJ and a downrange kinetic impact of energy of over 160 mJ, see also Project HARP. By firing smaller projectiles at extremely high velocities, railguns may yield kinetic energy impacts equal or superior to the destructive energy of 5/54 caliber Mark 45 gun naval guns, which achieve up to 10 mJ at the muzzle, but with much greater range. This decreases ammunition size and weight, allowing more ammunition to be carried and eliminating the hazards of carrying explosives or propellants in a tank or naval weapons platform. Also, by firing more aerodynamically streamlined projectiles at greater velocities, railguns may achieve greater range, less time to target, and at shorter ranges less wind drift, bypassing the physical limitations of conventional firearms. The limits of gas expansion prohibit launching an unassisted projectile to velocities greater than about 1.5 km per second and ranges of more than 50 miles from a practical conventional gun system. Current railgun technologies necessitate a long and heavy barrel, but a railgun's ballistics far outperform conventional cannons of equal barrel lengths. Railguns can also deliver area of effect damage by detonating a bursting charge in the projectile which unleashes a swarm of smaller projectiles over a large area. Assuming that the many technical challenges facing fieldable railguns are overcome, including issues like railgun projectile guidance, rail endurance, and combat survivability and reliability of the electrical power supply, the increased launch velocities of railguns may provide advantages over more conventional guns for a variety of offensive and defensive scenarios. Railguns have the potential to be used against both surface and airborne targets. Although many arguments in favor of M-guns revolve around the assumption that greater muzzle velocity is always better, this is open to challenge. Parametric relationships between range, payload weight, and launch velocity show that this is not a strong argument for many suggested M-gun applications. For example, due to lower aerodynamic drag at launch, a slower but heavier projectile may actually fly farther than a lighter, faster one, making the velocity limitations of chemical propulsion perfectly acceptable. In addition, explosive fragmentary warhead lethality is largely unaffected by velocity and does not require more demanding hit-to-kill guidance electronics that may not survive extremely high gun launch accelerations. Significantly, explosively formed penetrator and shaped charge warheads already drive what is technically a kinetic energy penetrator to velocities well in excess of M-gun launch capabilities, up to 8 km per second for a shaped charge, upon detonation with the target, and it has been demonstrated that with respect to armor penetration, increased impact velocity much above 2 km per second does not necessarily result in a deeper hole, although the crater may be wider as more energy is deposited with increased impact velocity. The first weaponized railgun planned for production, the General Atomic Splitzer system, began full system testing in September 2010. The weapon launches a streamlined discarding sabot round designed by Boeing's Phantom Works at 1,600 m/s, 5,200 feet/s, approximately Mach 5, with accelerations exceeding 60,000 gn. During one of the tests, the projectile was able to travel an additional 7 kilometers, 4.3 miles, downrange after penetrating a 1/8-inch, 3.2 millimeters, thick steel plate. The company hopes to have an integrated demo of the system by 2016 followed by production by 2019, pending funding. Thus far, the project is self-funded. In October 2013, General Atomics unveiled a land-based version of the Blitzer railgun. A company official claimed the gun could be ready for production in 2 to 3 years. Railguns are being examined for use as anti-aircraft weapons to intercept air threats, particularly anti-ship cruise missiles, in addition to land bombardment. A supersonic sea-skimming anti-ship missile can appear over the horizon 20 miles from a warship, leaving a very short reaction time for a ship to intercept it. Even if conventional defense systems react fast enough, they are expensive and only a limited number of large interceptors can be carried. A railgun projectile can reach several times the speed of sound faster than a missile. Because of this, it can hit a target, such as a cruise missile, much faster and farther away from the ship. Projectiles are also typically much cheaper and smaller, allowing for many more to be carried. They have no guidance systems, and rely on the railgun to supply their kinetic energy, rather than providing it themselves. The speed, cost, and numerical advantages of railgun systems may allow them to replace several different systems in the current layered defense approach. A railgun projectile without the ability to change course can hit fast-moving missiles at a maximum range of 30 nmi, 35 miles, 56 kilometers. As is the case with the Phalanx CIWS, unguided railgun rounds will require multiple/many shots to bring down maneuvering supersonic anti-ship missiles, with the odds of hitting the missile improving dramatically the closer it gets. The Navy plans for railguns to be able to intercept endo-atmospheric ballistic missiles, stealthy air threats, supersonic missiles, and swarming surface threats. A prototype system for supporting interception tasks is to be ready by 2018, and operational by 2025. This time frame suggests the weapons are planned to be installed on the Navy's next-generation surface combatants, expected to start construction by 2028. B Systems was at one point interested in installing railguns on their future combat systems manned ground vehicles. This program was the U.S. Army's third attempt to replace the aging M2 Bradley. India has successfully tested their own railgun. Russia, China, and Turkey's defense company Aselsan are also developing railguns. Helical Rail Gun. Helical railguns are multi-turn railguns that reduce rail and brush current by a factor equal to the number of turns. Two rails are surrounded by a helical barrel and the projectile or reusable carrier is also helical. The projectile is energized continuously by two brushes sliding along the rails, and two or more additional brushes on the projectile serve to energize and commute several windings of the helical barrel direction in front of and/or behind the projectile. The helical railgun is a cross between a railgun and a coil gun. They do not currently exist in a practical, usable form. A helical railgun was built at MIT in 1980 and was powered by several banks of, for the time, large capacitors, approximately 4 farads. It was about 3 meters long, consisting of 2 meters of accelerating coil and 1 meter of decelerating coil. It was able to launch a glider or projectile about 500 meters. Plasma railgun. A plasma railgun is a linear accelerator and a plasma energy weapon which, like a projectile railgun, uses two long parallel electrodes to accelerate a sliding short armature. However, in a plasma railgun, the armature and ejected projectile consists of plasma, or hot, ionized, gas-like particles, instead of a solid slug of material. Marauder, magnetically accelerated ring to achieve ultra-high directed energy and radiation, is, or was, a United States Air Force research laboratory project concerning the development of a coaxial plasma railgun. It is one of several United States government efforts to develop plasma-based projectiles. The first computer simulations occurred in 1990, and its first published experiment appeared on August 1, 1993. As of 1993, the project appeared to be in the early experimental stages. The weapon was able to produce donut-shaped rings of plasma and balls of lightning that exploded with devastating effects when hitting their target. The project's initial success led to it becoming classified, and only a few references to Marauder appeared after 1993. The project may or may not have been scrapped sometime after 1995. Tests. Full-scale models have been built and fired, including a 90mm, 3.5 in bore, 9 megajoule kinetic energy gun developed by the U.S. DARPA. Rail and insulator wear problems still need to be solved before railguns can start to replace conventional weapons. Probably the oldest consistently successful system was built by the UK's Defence Research Agency at Dundrennan Range in Kirkcudbright, Scotland. This system was established in 1993 and has been operated for over 10 years. The Yugoslavian Military Technology Institute developed, within a project named Edo Zero, a railgun with 7 kJ kinetic energy, in 1985. In 1987 a successor was created, Project Edo 1, that used projectile with a mass of 0.7 kilograms, 1.5 pounds, and achieved speeds of 3000 m/s, 9,800 feet/s, and with a mass of 1.1 kilograms, 2.4 pounds, reached speeds of 2,400 m/s, 7,900 feet/s. It used a track length of 0.7 m, 2.3 feet. According to those working on it, with other modifications it was able to achieve a speed of 4,500 m/s, 14,800 feet/s. The aim was to achieve projectile speed of 7,000 m/s, 23,000 feet/s. China is now one of the major players in electromagnetic launchers. In 2012 it hosted the 16th International Symposium on Electromagnetic Launch Technology, EML 2012, at Beijing. Satellite imagery in late 2010 suggested that tests were being conducted at an armor and artillery range near Baotou, in the Inner Mongolia Autonomous Region. United States Armed Forces. The United States military is funding railgun experiments. At the University of Texas at Austin Center for Electromechanics, military railguns capable of delivering tungsten armor-piercing bullets with kinetic energies of 9 megajoules have been developed. 9 mJ is enough energy to deliver 2 kilograms, 4.4 pounds, of projectile at 3 kilometers per second, 1.9 ms/s. At that velocity, a sufficiently long rod of tungsten or another dense metal could easily penetrate a tank, and potentially pass through it. See APFSTS. Naval Surface Warfare Center Dahlgren Division. The United States Naval Surface Warfare Center Dahlgren Division demonstrated an 8 mJ railgun firing 3.2 kilograms, 7.1 pounds, projectiles in October 2006 as a prototype of a 64 mJ weapon to be deployed aboard Navy warships. The main problem the U.S. Navy has had with implementing a railgun cannon system is that the guns wear out due to the immense pressures, stresses and heat that are generated by the millions of amperes of current necessary to fire projectiles with megajoules of energy.
Please subscribe and thanks for watching.